In this lecture, we will talk about thermal and electrochemical combustion. Okay, so this might be a new term, electrochemical combustion. I will clarify what I mean by that in this lecture. And specifically, we'll be looking at enthalpy and Gibbs free energy changes involved in combustion process. In the previous lecture, we had introduced two topics. One is we had introduced the grand challenge of your generation. I feel energy is one of the grand challenges of your generation. The energy demand is going to increase significantly. How do you generate clean energy without generating a lot of CO2, generating energy in a sustainable manner is going to be a defining problem of your generation. So I hope you get interested in these topics, and in some ways, thermodynamics is part of energy science and engineering. So it's important that at least you have an idea of what are the problems, relevant problems. Okay, so as I said, in energy itself is not a problem. How do you, lots of sunlight is available to you. How do you convert that energy into a usable form? How do you store that energy? So energy conversion and storage is the grand challenge. I am sure in every one of your department, whether it's mechanical engineering, chemical engineering, or aerospace engineering, there are specialized courses that talk about energy. It's good that you take these classes. We looked at specific aspects of thermal combustion. So we wrote the first law as is relevant to combustion. We defined enthalpy in a particular manner, and we said we clarified these terms. Okay, so how do you write the enthalpy of a particular chemical component? Rated it to heat of enthalpy of formation, and then there is delta H term. Okay, so how do you convert from the standard state of a compound, let's say water, liquid at 25 degrees centigrade and 1 atmosphere, how do you convert that to vapor? That is the enthalpy of this state, okay, vapor, that is the heat of vaporization. And then you may be dealing with water vapor at a higher pressure and different temperature. That is corresponds to this particular term. Okay, so you should understand the meaning of this term. It's very critical. And then the rest of the things follows. Just the first law of balance. And then there are a few technical terms you should be aware of. One is the higher heating value and lower heating value. These are all fairly commonsensical. That is, if you, the products of combustion, let's say in this case, water, if it's in the form of a liquid, the act of conversion of vapor, water vapor to liquid itself involves hydrogen bond formation and some further energy release. So that corresponds to higher heating value. But if the product of combustion is just water vapor, then that corresponds to lower heating value. So combusting H2 and O2, H2 with O2, forming H2 in the vapor state will give you lesser heat. But if you form water, you will get more heat. And then you also define something called adiabatic temperature. That is, if there is no work and heat interaction, all the heat that is being generated goes towards heating the products of combustion. Okay, so there is a maximum temperature that the products of combustion can reach. Most of the time, the combustion is incomplete because the amount of oxidant that is provided is not sufficient to completely convert the fuel. So stoichiometric conversion of the fuel is not fuel into completely oxidized product is not possible. So you have incomplete combustion, or you may also have heat loss. Okay, so the condition might not be entirely adiabatic, or you can also have the product of combustion can also dissociate. We may form free radicals and so on. Okay, so all these things decrease the temperature of the products that can be formed. So it's not at the maximum temperature. So all these things we covered in the last lecture. We will move on from enthalpy changes to entropy and, of course, the free energy change, which is the most important thermodynamic potential function that is of relevance. So what we're interested is in entropy changes involved in reacting systems, chemically reacting systems. So again, because entropy is not a conserved variable, we can write a balance equation involving entropy generation term. So all the entropy transfer terms via heat transfer is accommodated in this term, and there is an entropy generation term, and then there is a delta S of the system, which involves entropy of the products minus entropy of the reactants. Okay, so this is a general balance equation for something that's not a conserved variable, okay, some conserved quantity. We wrote a similar equation for Exergy too. So even in adiabatic case, when supposing there is no heat transfer, heat interaction between the system and the surrounding, you can have equation which corresponds to the second law of thermodynamics. S product minus S reaction is greater than or equal to 0. So this is like saying it's an extremal condition, right? So at equilibrium, delta S is 0, but the general condition for delta S is greater than or equal to 0. Here, the delta S arises because of a chemical reaction. So this is the extremal form of second law of thermodynamics for a chemically reacting system. So how do you implement all these things in practice? So we had seen this table in the previous lecture when we had focused on just the enthalpy of formation. In this lecture, we want to clarify this term called absolute entropy. Okay, so this is important for computing entropy changes. So by second law of thermodynamics, as temperature goes to 0, entropy reaches a constant value. We can interpret in terms of microscopic formulation. It will make sense why there is the third law of thermodynamics. And if the degeneracy is 1, then entropy goes to 0 as temperature goes to 0. So this constant in most of the engineering thermodynamic, in the context of engineering thermodynamics, we assign a value of 0 to this constant and say at T equal to 0, every component has an entropy T equal to 0. Okay, so every pure component has an entropy T equal to 0. So that is the datum we typically refer to, and absolute entropy is with reference to that particular datum. Okay, that entropy is 0 at T equal to 0 is the datum we are going to use. And when you specify entropy, let's say in this case 298 Kelvin and 1 atmospheric pressure, that's what is called absolute entropy. Okay, so that's the definition you ought to be knowing. And we know how to compute entropy of solids, all these things. We've dealt with these things in the previous lectures. So typically you look at TdS relationship and calculate the entropy of solids, liquids, and gases. And then that's the definition of absolute entropy. And how do you approximate entropy changes? The approximation we are all the time referring to is whenever you have a vapor in combustion, chemically reacting system, and the most important chemically reacting system in the context of engineering thermodynamics is combustion. So you have things in the vapor phase. So you use the ideal gas approximation and then compute based on heat capacities and so on for different substances. Entropy has been tabulated. Okay, so there are tables available which gives you the entropy of different substances at 1 atmospheric pressure. Okay, that's the standard state. This is well tabulated. And then you may want entropy at higher pressure, for example, So that again, we are going to use an ideal gas approximation and get the entropy at the temperature of interest and pressure of interest using this tabulated value and using the ideal gas approximation. Okay, so by now you should know how do you go from a TDS relationship to get a sense of tabulated values, and in the TDS relationship, if you use the ideal gas approximation, how do you get this term? That should be clear to you. So this is for a single component system. The pressure of the system is entirely made by one component. However, this similar approximation can be utilized for a multi-component system also. You use the partial pressure of, let's say, Pi, and then if you know the mole fraction of the particular component I, you can, from the total pressure, you can get to the relevant partial pressure, and again you can use the ideal gas approximation and get to the entropy of the component of interest. Okay, so this is the partial pressure of the component of interest. This is the partial entropy of the component of interest. Okay, so this is the way we approximate entropy, and using this you can calculate entropy changes. All right, so we will look at an important relationship that has a lot of consequence. As I said, when I started the previous lecture, we are going to be looking at a lot of power generation. Okay, in the previous lecture and the series of lectures, we're going to be looking at power generation. So power generation has to do with combustion. When you say combustion, we are always referring to an exothermic chemical reaction. Okay, so from this combustion, you can get two kinds of useful quantities. Sometimes heat is the quantity that is useful, or you can also get work. Okay, so both are very useful. So whenever we are talking about work, we have to undertake an exergy analysis. Okay, so exergy is the work potential of the system. So supposing the reactants have gone from the reactant state to a product state, typically, let's say this reaction has occurred at the temperature and pressure of the ambience. Okay, so that's one way of undertaking the chemical reaction. So that's why the potential of relevance at constant temperature and pressure gives free energy. So we'll see why that's going to be important. So the exergy decreases when you go from reactant to products. And this exergy change, okay, is associated with entropy generation and some exergy destruction. And we can also correlate it to reversible work. Okay, so let's see how we are going to think about all these things. So it's good for you to refresh how we looked at exergy analysis of a steady flow system. Okay, so there we talked about exergy of at the inlet and exergy at the outlet. Okay, things are, for a flow system, things are flowing in and things are flowing out. This is the outlet exergy and this is the inlet exergy. So that has an enthalpy, and T0 is the ambient temperature, and so on. Okay, so we had already done this when we dealt with exergy balance of a steady flow system. So there we wrote this equation. Just please go and take a look at that, the basis behind this equation. So here what we have is, for a chemically reacting system, you don't have heat exchange with the reservoir. Okay, so this is a general balance equation, Exergy balance equation we wrote. However, for this system, you don't have heat transfer with the reservoir. Okay, so this term happens to be 0. Therefore, we can write the reversible work that you can obtain by this Exergy balance. So here the inlet Exergy is from the reactants. Okay, so on the outlet Exergy is from, even it doesn't go to the system, go outside the system. So we are, let's say, considering a closed system. What we have put in is the Exergy of the reactants, and what you get out is the Exergy of the products of the reactants. Okay, so so that's the way we are going to relate to the maximum work which you can get from the system, right? So note, yeah, all right. So from here, where did we go? So in the previous lecture, we defined how do you define the enthalpy of the reactants and products. We had broken that down into enthalpy of formation at some standard state, and then it may change to particular, there can be a phase change, and then the particular component are changed to a particular pressure and temperature of interest. So from here, we translated this particular term into this term, and the other terms are the same, right? So, and then what do we know? Okay, so we can, once we have this particular form, we know the definition of Gibbs free energy. Okay, in this case, what is important to understand is the reactants and products are at the same temperature and pressure as that of the environment. Okay, so once that's the definition of the system, you can convert these terms in terms of Gibbs free energy. Okay, so I can write these particular terms in terms of Gibbs free energy. Therefore, I can rewrite this particular term in the following manner. So all I have is the maximum work that you can obtain from the system, from a chemically reacting system, is because of the change in free energy. Let's say you can consider it per molar basis also. So this is the number of moles, GI of the reactants, the number of moles of the products, times the Gibbs free energy of the products. Okay, so this delta G, okay, is the reason why you get work out of the system. Okay, so if there is an exothermic reaction, delta G will be negative. Negative is a positive number. If the work you get is a positive quantity, right? So it's important to understand the logic behind this derivation. This is better elaborated in this textbook compared to Schengel and Bullis. So you can please look at, for this particular section, please look at this book, and I will post these 2 pages in the resource section of in the class website, okay, in the MOOCit website. So please go through this particular definition. Okay, so where we started, okay, and then how did we arrive at this? Okay, so all these things are related to Exergy balance, which we have already done, and then all we have done is rewrite enthalpy using this expression, which we derived in the previous lecture, and the rest are should be familiar to you. Okay, so what is interesting is
when you have a chemically reacting system, it is not at equilibrium. Okay, so this S generation is because of difference in the entropy between the products and the reactants. Okay, so I suppose there are questions in this slide, and we can have a more elaborate discussion during our discussion hour, but depending on the questions you have. Okay, so I'll address this again in the discussion. All right, so this is an important relationship. Delta G is equal to delta H of the reactants minus T delta S of the reaction. Okay, so this is a very important formula, and that formula has to be connected to the maximum reversible work you can obtain from a chemically reacting system. There's a lot of implication. Okay, so what is the implication? So knowing what exothermic reaction is being conducted gives you an idea of what is the maximum work you can get from the system. For example, in this case, we have carbon oxidized by oxygen to form CO2. This is an exothermic reaction. So if you look at the free energy of carbon, that's the standard state, we assign a free energy of 0. Oxygen is the standard state, you assign a free energy of 0. But carbon dioxide, there are new chemical bonds, strong chemical bonds that are formed. So it has a negative number. So that means it's an exothermic reaction. So that is what goes in here. And there are small differences because I got for this from one source and these tables are from slightly different source, but approximately they're one and the same. So that tells you what is the maximum work you can obtain from undertaking an exothermic chemical reaction. So where do you get such work? Okay, so one of the most straightforward manifestation of work from an exothermic reaction is the electrochemical combustion. So what do you mean by that? Electrochemical combustion is done in a fuel cell. It is an electrochemical gadget. Both fuel cell and batteries are electrochemical devices that are not constrained by Carnot efficiency. We have already mentioned this in the early part of the class. Only when there is thermal energy to work conversion, you are limited by Carnot efficiency. Okay, in principle, there is no Carnot efficiency for fuel cells and batteries, because what you're doing here is you are converting chemical energy, exothermic chemical energy, the delta G of chemically reacting system, and obtaining electrical work. Okay, so in the most common fuel cell is the hydrogen fuel cell. You might have heard something called PEM fuel cell. Okay, polymer electrolyte membrane fuel cell, or proton exchange membrane fuel cell. PEM fuel cell, that's what it means. So typically, what is the fuel? Hydrogen is the fuel and oxygen is the oxidizer. There is electrochemical combustion that is taking place, which gives rise to delta G being negative because it's an exothermic reaction. And this exothermic reaction is converted to electrical work. And the formula for electrical work is NFE, and N is the number of electrons involved in this electrochemical reaction. F is the Faraday constant, and E is the electrochemical potential, open circuit potential that you can get by undertaking this electrochemical combustion. Okay, so this is a very, very important way of energy transformation, because it is environmentally very friendly. Okay, so there's no pollution involved because this is a carbon-free fuel, and you are generating electrical work unconstrained by Carnot efficiency. However, it has its own challenges. The materials of construction that is being utilized, the anode, cathode, and the electrolyte might be expensive. It may involve platinum electrocatalyst. This is right now the electrolyte that is used is a monopoly by a particular company. So there is a lot of research that goes into this. And how do you get hydrogen? That's also not trivial. Okay, and how do you store hydrogen? That's also not trivial. So there are many different forms of fuel cell. As opposed to hydrogen, which is a gas, you can also have methanol. Okay, methanol is a liquid, therefore it is more easily stored. However, the chemical bonding changes that occur in a methanol fuel cell is more challenging. So the maximum voltage which you get is lesser because the delta G of combustion, the exothermicity of this particular reaction, that is methanol oxidation, is lesser. Okay, so therefore the potential which you get from a methanol fuel cell is also lesser. Okay, so these are all very important areas of energy research. These are frontier areas. So even though I've talked about fuel cell, the operation of a battery is also very similar. Here, the main difference is that fuel is being continuously supplied in a fuel cell, but there's like a flow reactor. Okay, things are flowing in and things are flowing out. But in a battery, it's like a batch reactor. Okay, so there is, let's say, if you have a lithium-ion battery, there is an exothermic reaction, again, not constrained by Carnot efficiency. And because of the exothermic reaction, there's the corresponding delta G, you can get the maximum potential from a battery. Lithium-ion battery has a very high exothermicity because of certain electrochemical reasons. That's why the potential that you can get from lithium-ion battery is very high. Okay, so this is an important area of energy research, so you should be at least aware of this particular topic. So in the next lecture, we would look into certain aspects of phase equilibria. This is, again, a huge topic. We won't have time to look into all aspects of this subject, but we'll at least look at two specific things, a few specific aspects of phase equilibria, especially those involving chemical potential, phase rule, and Kirchhoff's equation. Thank you.